everyone, welcome to this video. In this video, want to discuss about the DC and AC Josephson effect. This is the part of the superconductivity. You know, the superconductivity is a state of the metal at which the current flow is very large. That is, the resistivity tends to zero below a certain temperature called critical temperature. At first, 1911, it was observed by commanding Ohms for the metal Hg, and after that very research obtained for different material to obtain the high TC, that is the critical temperature superconducting for use in the daily life application. There is various application. Okay, so in this superconductor there is a special effect. This is called Josephson effect. We want to know about this effect in this video. Okay, so start. If there is a superconductor, suppose this is a superconductor, this is a piece of a superconductor, this is a superconductor, and you connect a external voltage source. If we connect a external voltage source with this superconductor, right, and to measure the current and voltage, connect a ammeter and parallel with the voltmeter. Okay, so this is a superconductor, connect a external voltage source with an ammeter and the voltmeter. Okay, what will be the happen of the value of the voltmeter? Because there is a current flow is tends to infinity, total current flow goes through here, and the resistivity tends to 0. So from V equals to IR, since R is equals to 0, that's why voltage reading of this voltmeter will be 0. So this reading will be 0 reading. Clear in this case. Now if we break this superconductor in two part, or if we collect contact to superconductor, like this is a superconductor 1, and another superconductor, this is another superconductor 2. In the gap, this gap is nearly 1 centimeter. If this gap is only centimeter and the situation are the same and the other situation are the same, that is, the there is a voltage source and there is a ammeter, and connect the voltmeter to measure the voltage. Okay, so you can see that there is no current flow and the voltmeter gives you the voltage which is measured in the, so this is the maximum value. Okay, maximum value. Okay, this is no problem. But if we close these two nearly to 1 to 5 nanometer, if we close these two superconductor 1 and superconductor 2 in the gap nearly 1 to 5 nanometer, then what happen? Then you can see that this is a uh, EMF, applied EMF, this is the ammeter, and connect with the external voltmeter. Okay, so the value of this voltmeter again tends to 0. Why? This, there is a gap present, but the current will be, voltage will be 0. That means they are flowing the current, flow the current, right, flow the current. So the current flow is happening due to tunneling. Okay, so this current flow is happening due to single electron tunneling or the quantum tunneling, quantum tunneling effect, or you can say this is a Josephson tunneling. This is also called as the Josephson tunneling. Josephson tunneling. This effect also known as Josephson tunneling. Okay, so this is known as Josephson tunneling because there is a gap, but also the tunneling was happen. That is called Josephson tunneling. This is a quantum mechanical tunneling. You all know that. And this effect is known as the Josephson Josephson effect, and the gap is known as or this junction is known as the Josephson junction. This junction is known as Josephson junction, right? Josephson junction. This is the Josephson effect. Okay, so there is a gap between two superconductor bar also they flow current. This is the Josephson current, and the effect is Josephson effect, and the junction is known as Josephson junction, and the tunneling is known as Josephson tunneling. Okay, there are three types of Josephson junction are available. Types of Joseph Josephson junction. There are three types of Josephson junction are available. Number one, SIS, that is superconductor insulator superconductor. This is superconductor, this is insulator superconductor. Superconductor, I want to write in the middle. This is the difference. Insulator. Number two is S. The middle S is the superconductor. Superconductor. The other property. Number three is S. N for non-superconducting metal. Non-superconducting metal. Superconducting metal. In these three cases, or in these three junctions, Josephson effect or Josephson effect observed. Now, if we interest about this junction is nearly 1 to 5 nanometer. About this junction, if we interest about the junction, there are two types of Josephson effect are happening. Types of Josephson effect. Josephson effect. There are two type of Josephson effect happening. Number one, DC Josephson and AC Josephson. AC Josephson. Okay. What is the basic difference? In DC Josephson, that is when we apply, there is a gap. When we apply a voltage, the current flow originate, and if we connect the voltage or remove the voltage, remove external source, then there is a flow of current in between this current is constant current, the current flow within this which is constant current, which is constant, sin delta, which is constant. We will be derive this expression. In this case, there is no external source, but there is a DC current flow. Okay, this is the DC Josephson effect. In the other side, if there is a apply a DC voltage, if there is a apply a DC voltage apply, if there is DC voltage apply, then there is a oscillation occur. The I equals to I0 sin delta, this is delta 0 minus omega t. So there is a omega t, that is the frequency. This is the AC Josephson frequency, that is there is a oscillating current flow. Okay, this is the AC Josephson. Apply DC voltage and there is a oscillation, that is the oscillating current flow. That's why I call this is a AC Josephson. I think clear. In case of DC Josephson, there is no external source apply, but there is a flow of constant current between these two superconductor 1, superconductor 2. But when we apply a DC voltage source in external, then there is a oscillating current flow between these two superconductor. This is the AC Josephson effect. Clear? Now we try to derive these two expression quantum mechanically. Okay, at first comes into DC Josephson effect. When two superconductors psi 1 and psi 2 taken this two superconductor, and in between this is a insulator. So the wave function of the uh, Cooper pair. Actually, this current flow due to Cooper pair. The current flow due to Cooper pair in the superconductor. Current flow due to Cooper pair. Current flow due to Cooper pair through superconductor. Through superconductor. Okay. And the wave function of this current flow is written as this. There n is the number density of the carrier, and this is called the phase. This portion is phase portion, and this is the number density. This is for semiconductor 1, sorry, superconductor 1, and this is for superconductor 2. So if we want to write the Schrodinger equation of these two, so you can say that is I cross H del psi del t. Schrodinger equation is H psi, right? H is nothing but the energy term, okay. So if we multiply this T with this energy term, gives you this is the transfer coefficient. Coefficient means the transfer per unit time. There is a per unit time, right? Per unit time means the unit will be second inverse. Per unit time means there is second inverse or hertz. So this is the hertz. So if we multiply the H cross with this T, if we multiply with the H cross, and this is the frequency and this is the H into frequency, you know, this is the equivalent to energy. Clear? Dimensionally you can say this is a energy. That's why we replace the H by H cross T. Clear? And the transfer towards the psi 2, that's why this written as this. So H cross T is a energy term, and the psi will be psi 2 because it's transferred to another side. Clear? So if we just I taken as in right hand side, you can see here. Similarly for semiconductor 2, you can write this H cross T psi 1. This is psi 2, this is psi 1, and this is also written as this. This is a true equation. And since psi equals to this, so if we derivative of this psi, this is partial derivative, you can do that easily and put in this derivative in those two equation 3 and 4. So if we using 5 and 5 into 3, if you use 5 into 3, you just put this value, you got this expression delta, where delta is the phase difference. The phase difference, right? The delta is the phase difference between the Cooper pair of two, between Cooper pair transmission of two superconductor. Okay. Just after that, if we compare the real and imaginary part, the real part will be this, so this will be equal to that, and the imaginary part will be that. So the number density and phase will be written on for in the superconductor 1, the site 1. Similarly, just use this 5 in 4 in this equation, you and then compare the real and imaginary, you also get these two equation. You can see this is like to similar, and n1 dot is equals to minus n2 dot number 1, and number 2 will be del n1 by del t equal to minus del n sorry, this can be written as like that. This is the persistent current, this signify persistent current. Now if there is same type or the identical same type semiconductor, sorry, this is not semiconductor, this is superconductor, this is superconductor superconductor, or you can call identical, then the number density will be nearly equal. So just equation 8 you can say, theta 1 and theta 2, this is identical, n1 into are same, so this cancel out, minus t cos lambda, and in case of theta this is also minus t k lambda, so these two are identical. So you can say this is nothing but this is nothing but del t of theta 2 minus theta 1 equals to 0. So theta 2 minus theta 1, or you can say this is theta 1 minus theta 2, theta 1 minus theta 2 will be 0. So theta 1 minus 2 theta 2 will be constant. Okay, since this theta 1 minus theta 2 is constant, that's mean you can say the current flow, you can say the current flow, that is the current flow, current flow I is proportional to del n del t or n dot, right, and n dot is nothing but the proportional to sine delta. For n1 dot or n2 dot, you can see this is proportional to sine delta. Since delta is constant, so this will be also constant. So I is nothing but I0 sine delta. Since delta is constant, so I can say constant. That's mean there is flow of the DC current, flow of DC current. Okay, so there is flow of DC current. That's why this is called the DC Josephson effect. DC Josephson effect. This is called DC Josephson effect, in which the current flow within the material or the superconductor will be constant, since there is no external voltage source. We do not apply any voltage term in this equation. The voltage term will be 0 in this Schrodinger equation. Okay, so no external voltage source, they are only without any external voltage source there is a flow of the DC current, direct current. That's why this is called the DC Josephson effect, and this current will be constant. By using this quantum mechanical wave function, we can prove this one. Goes to the AC Josephson effect. In the AC Josephson effect, we will apply a DC voltage source. If we apply external DC voltage source, what happen? The total energy will be minus 2E, because there is a QV, total energy will be QV, and Q is 2E. Why twice E? Because there is a Cooper pair, always two electron are along with Cooper pair. Because of Cooper pair, Q will be minus twice E. Okay, so that's why the voltage for two total difference is minus 2 ev, so we can take minus ev and plus ev, just that the difference will be minus 2 ev. Okay, so at that point minus ev and that point plus ev, so final minus initial will be the difference, from that side to that side will be minus 2 ev. So if you put the in the Schrodinger equation in the same manner, this is nothing but the, in the previous, that is the, this term is actually energy term, right? This is energy term and this is the potential energy term. So if we put this one for in psi 1 side, that is a superconductor 1, and for superconductor 2, okay, and this derivation taken from the DC Josephson effect, and put this value in this equation 1, you got the relation like that. These two are relation was obtained, and you can see this relation is nothing but identical with the additional term. This term was added. This is the additional term, compared to DC Josephson effect, compared to DC Josephson effect. Clear? And the similar manner in the second case, that is the superconductor 2, you can just put the same manner, just go through this calculation, you can get the same expression like super DC Josephson effect with the additional term. This is the additional term, additional term, additional term, uh, compared to DC Josephson effect. Clear? Now from 3 and 4, we can say there is a n1 prime, sorry, n1 dot with nothing but the n2 minus n2 dot, just like this is there is a minus. Okay, so n1 dot is nothing but minus n2 dot, that is nothing but this is the current flow one side to another side, these are the same. Okay, and from the difference of these two you can write this is nothing but just put this value theta 1 dot and put the value of theta 2 dot. You can see there is a change in if I h cross, and the difference will be like that. So this if we integrate this, delta d equal to delta 0 minus 2 ev into t, this is retained as omega. Omega is nothing but angular frequency, so the frequency of oscillation will be f is to a omega by 2 pi. So this is the value of angular frequency of the AC Josephson effect. AC Josephson effect, this is the angular frequency. Okay, so since you know the current flow, the current flow AC Josephson, since AC current flow is nothing but current is nothing but proportional to del n del t n1 or n2, will be like that. And you can see the n1 and n2 both are proportional to sine delta, so this can be written as sine delta. So I is nothing but I0 sine delta, and delta is nothing but delta 0 delta is nothing but delta 0, this can be delta 0 minus omega t. This is a oscillating oscillating part, not a constant. So this can be says this is a AC current flow or the RF current flow, oscillating current flow through the through superconductor sorry through superconductor. Okay, that's why this is called a AC Josephson effect, because with applying the DC voltage within the Josephson junction, you can get the AC current flow within this superconductor in between two. I think clear. If there is any query, always go through the comment box and comment in the comment. Okay, there is a problem, you can solve this, just go through this question. A DC battery of this is a DC battery applied across it through a AC Josephson. Since there is apply a DC battery, that's why occurred the AC Josephson. Find the frequency of oscillation. Just put the relation, f is nothing but 2 ev by h, and you got the value like that. Very simple. Okay, so thank you, we will meet in the next video as soon as possible.